So, now there are more improvisation, as I told that okay, that was beginning, and then geometric Brownian motion is more or less pretty much understood, but that has some limitations. So, in 1993 Stephen L. Heston, okay, this is the photo of Heston I obtained from open domain. So, L. Heston model volatility. Okay, so volatility is pretty much like just here for this sigma appears, correct, this sigma, this sigma is called volatility, okay, the coefficient of Brownian motion. So, here what he did, he allowed volatility coefficient to also vary over time as also a stochastic process, okay, given by a stochastic differential equation known as CIR process, Cox Ingersoll Ross process. Okay. So, he has obtained a generalized BSMPD involving an extra parameter. So, that was his work. So, we are interested about looking at the SD what he came up with, okay, or what he proposed. So, also obtained a closed form expression of our European options. These are success stories. Okay, the model gives an incomplete market, okay, etc. And however, the calibration of the model is challenging. So, we come to this thing, okay, the small change of the process. So, this is the stochastic differential equation as earlier. Here we add mu, also we now have mu. Earlier we had sigma here, instead of sigma now we have a square root of V t, which is this is time dependent, okay, square root of V t, where V t is a stochastic process which solves another stochastic differential equation. dVt is equal to, so some drift parameter which also involves Vt, okay, affine linear function dt plus, so here some constant sigma times square root of Vt dw prime t. Okay. So, this unknown appears here also. Okay. So, here also unknown appears here, the coefficient, but here unknown also appears, but here unknown appears as a linear function, correct. The coefficient is a linear function of s. Here this coefficient is not linear function of v, correct. It is a square root of this, and the coefficient here is of course constant. Okay. So, this we call volatility of volatility. So, this appears like volatility of this, correct. So, volatility of volatility we call this. Okay. And then this w and this w prime need not be the same, they could be two different Brownian motion, they could be independent, they could be correlated. So, if they are correlated, so dwt dw prime t is rho dt, rho is the correlation coefficient. So, that is the market traders they believe that this rho should be negative term. Okay. That is a different story, that why, I mean, or how they believe and why do they believe that. So, that is the model. Okay. So, now imagine that we have such type of stochastic differential equation. Okay. Forget about this, we just look at this thing. Okay. So, how can we assure that this has a solution? Okay, how can you assure this has a solution? Because it turns out that for this equation it is not possible to get any closed form solution. Okay, one can write down the solution of this equation in terms of elementary functions. However, this equation was largely studied, we call this CIR process. Okay, this is studied because of its very interesting feature. Okay, so let us look at the feature of this process. Okay. Without solving it, just looking at this equation, we can actually understand how does it behave little bit. Okay. So, that we are I am going to discuss here. Once one get this Vt, then using this Vt one can solve St. So, here this is actually system of stochastic differential equation. So, one should perceive this as system of stochastic differential equation. It has two unknowns, okay, St and Vt, and two unknowns, two equations. Okay. So, now let us see what does it do. So, here all this term has some particular meaning. So, the kappa is called speed parameter, theta is called long run mean, and this sigma is called the volatility of volatility. Okay. So, now we try to understand that how Vt moves. Okay. imagine that theta is some positive constant, kappa is some positive constant, okay, and your Vt is very large. So, at some time t Vt become very large, okay, very large, much larger than theta. Then what would happen? So, since Vt is very large and larger than theta, so theta minus Vt would be negative. Since theta minus Vt is negative, so that means the drift is negative, okay. So, small change of the dVt would be a negative term times dt. So, it would force to the lower side. So, minus d, okay, negative term dt. So, that means the next change would be smaller than Vt. So, Vt plus delta could be less than Vt. However, it is not as simple as that, because it is not OD, it is SD. Some other term is also involved. This is a Brownian motion, okay, that this dWt could be positive or could be negative, okay. Although this coefficient is positive, of course, there is no doubt about it, but this could be positive or negative, okay. Now, although this term is negative, okay, however, this term could be very high positive, because Brownian motion, the increments are like almost like square root of dt type, because dWt whole square is like dt, okay, that product table says that. So, when the number is very small, then their square root is actually larger than the number, correct. If a number is smaller than 1, the square root is actually larger than that number. So, here this term would be larger than this dt term, okay, would be dominant. So, there is some kind of fight between these two terms. However, if V is significantly large, then perhaps it would be able to win over it, okay, and then it would give a push towards the lower side, because then change of Vt is negative, that means the next V would proceed to the lower side. Okay. So, on an average it would come below. So, when it goes up, then there is kind of force to push it below. That we understand from this equation, okay. It would not directly come just like exponential function, but it would fluctuate, but on an average it would come down, because this part is negative, okay, and this part is positive, negative both, okay. Also another thing, when Vt is very large, the square root of Vt is not that large, okay. So, this coefficient would dominate over this coefficient also. So, that is also one thing one should take account of. Okay. Now, the other side, imagine that Vt is very small, very close to 0. What would happen? If Vt is very close to 0, so that means it is smaller than theta. So, this term would be positive, okay. This term would be positive, because kappa is anyway positive. So, dVt is positive, that means change would be upper side. However, story is not as simple as that, because there is some noise term also. So, the noise term, what is it going to do? Sometimes it could be positive, sometimes it could be negative. So, although it is going to push up, this can push down also, okay. However, it is multiplied with square root of Vt, okay. So, if Vt is very, very small, this is also a small quantity, okay. This is also a small quantity multiplied with the Brownian motion here, the incremental Brownian motion. However, if Vt is very small, square root of Vt is not that small also. So, it is not, intuitively we think that, okay, it would be able to push up, okay, but it is not very clear why it should win over, why it would not allow the process to go to negative side, okay. We understand just intuitively, very vaguely, that we do this, but there is a very clear sufficient condition, this we call failure condition. If the sigma is sufficiently small, that means sigma square is less than 2 times kappa theta, that assures non-negativity of V, okay. Because here we understand that if sigma is large, then although this is small, this Brownian motion, the negative term could push to touch to 0, okay. But this failure condition says that, okay, if sigma is sufficiently small, we actually can assure that it would remain positive, okay. Good. So, theta is something which is actually allowing us to do this analysis, because things is lesser than theta, then things are, the process goes up. If process is much higher than theta, then it comes down. So, that also gives the justification of the name, the theta is called long run mean, okay, long run mean. And kappa is speed. Why is it so? Because imagine the kappa is very large quantity, then even if beta is little more than theta, this term is kicked up, it is very high. So, it would sharply, the process Vt would sharply come down. So, speed of reverting around this mean is proportional to kappa, correct. So, it is coming from kappa. So, that is the reason we call kappa as speed. Okay. If kappa is very small, then actually Vt may allowed to go very large and may not, and then after that it would come back, and then the time it would take to come back etc., would be longer, okay, slower. So, that also justifies the name that kappa is called speed. And why this is called volatility, that is very clear, because this is coming from here. If sigma is 0, then there is no volatility, there is no fluctuation, this is just a ODE. How would that behave? It would be just exponential function, correct, the solution, and it would just if it starts from here, it would converge to this theta exponentially, okay, asymptotically, correct, and if it starts from below, it would just converge like this. Okay. Okay, so this is the understanding of SD. So, now we have some sort of feeling about what stochastic differential equation mean. And for one particular stochastic differential equation, which is for geometric Brownian motion, we have also solved that equation. We found that the solution in the closed form, but for this type of equation for which we cannot apply Ito's lemma here or something, we cannot do that. Okay. For that, we have discussed some properties, okay, using mostly hand wavy manner, because it is really far from our goal. However, we have quoted some theorem which is called Feller's condition, that studied this equation actually without solving it, that this sufficient condition for non-negativity. There are some other theorems also, like under another condition on sigma, if sigma is smaller than kappa by 2 rho plus square root of 2 positive part, because rho could be negative, correct. If rho is negative, then you do not take this, if it is positive, then only you take this. So, that thing assures that ST would be square integrable. Okay. So, these are the results what people study. So, what we have realized that for application purpose, stochastic differential equation do arise, and sometimes we can solve explicitly, sometimes we cannot. However, it is important to justify existence of solution, and sometimes after that we also study few more other properties, desirable properties of the stochastic process or the solution of the stochastic differential equation. So, next week onward we are going to discuss the topic of stochastic differential equation and the notion of its solution, strong solution, weak solution, etc. Also, that would allow us to enlarge the scope of the differential equation, the PDE we are discussing now, because we have discussed only those PDEs where the differential operator is just Laplacian, the second order differential operator is just Laplacian. Okay. However, when we are going to discuss this type of stochastic process, I mean beyond Brownian motion, this thing. Okay. So, for that would allow us to discuss some other Cauchy problems or Dirichlet problem, where the operator is not Laplacian, but some variable coefficients, second order partial differential operators. Okay. So, I stop here. Okay, thank you very much.